Okay, so for these problems, what we're doing is writing out mostly here the reasons, but there's also some statements in 5 and 7 that you got to write. And what it's asking you to do is not just write the theorem name, but you should be writing what that theorem actually is saying. So we've got that it's a parallelogram, and so we have to prove that A, C, and BD bisect each other at E. So basically, we're going to walk our way through it step by step, and I'm going to type it out. So I'll pause it and type it and then bring it back. Okay. 1, ABCD is a parallelogram. It's given. And 2, then we know that AB is parallel to DC. Well, this is the definition of a parallelogram. So, all right, and then you see they've got these angles. Angle 1 is congruent to angle 4, and angle 2 is congruent to angle 3. So we know that 1 and 4 are alternate interior angles, and we know that 2 and 3 are alternate interior angles. We don't necessarily know that they're congruent unless the lines are parallel. But we do know that because we established that in the last one. So what we're going to say here is that if lines are parallel, then alternate interior angles are congruent. So we can then establish that 1 is congruent to 4 and 2 is congruent to 3. Okay, and then we want to establish the statement they're asking us to establish is that AB, segment AB, is congruent to DC. Well, we know that the opposite sides of a parallelogram are going to be congruent, so we can just say that opposite sides of a parallelogram are congruent. Okay, and that's hanging over a little bit and over to 5, but that's all right. All that in blue is for 4. Now, 5D says, what are we trying to demonstrate? Well, angle side angle. Let's look at which angles they're talking about. We know, I'm just going to mark them. We know that this angle is congruent to this angle, alternate interior angles. And we know that this angle, let me do that again, this angle is congruent to this angle, alternate interior angles. And we know that this side, so as we established in the last bit, this side is congruent to this side. And then so we can then say that this triangle on the left, triangle AEB, is congruent to this triangle going from the blue angle to the center out. Blue angle AEB is congruent to, CED. AEB is congruent to CED. Triangle AEB is congruent to C. Okay, and then AE is congruent to CE, and BE is congruent to DE. Really, why did we establish that those triangles are congruent? Because then corresponding parts of congruent triangles are congruent, and we can do CPCTC for that. So let's just type that in. I don't think I have to make you go away. I can just type it. CPCTC. Great. And finally, then, what can we say? We can say what we needed to prove, which is that AC and BD bisect each other at E. Because that's the definition of a bisector, is that you get equal segments. So there you go. And I can't write the lines over top of these things, or I would mark them better as triangles, segments, and all of these things, but that's it. And you can see that we got to what we were trying to prove by first establishing that those sides were parallel, so that we knew that the alternate interior angles were congruent to each other. 2 was congruent to 3, 1 was congruent to 4. We knew that the green sides are congruent because parallelograms have opposite sides congruent. And then by angle side angle, we were able to establish that the triangle on the left is congruent to the triangle on the right, and therefore all corresponding parts are congruent, meaning each one of those diagonals is bisected at E into 2 equal segments, and that's what we were trying to prove. Yeah, that was a good one. Hope you enjoyed that one. The proofs are fun. They really make you try and puzzle out, what do I know? How do I apply it? And that's good mathematics to be able to do.